Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at our last lesson of chapter 4. This one is 4.3.3. This is also going to be a 2-day lesson, and this one is focusing on what happens when we are simplifying algebraic expressions where you've got positives and negatives being added together. We have some zero pairs that are going to be created from this situation. So we were introduced to zero pairs when we were talking about how to add integers together. And the same principles apply when we're adding algebraic terms together. So first off, the zero pair is what you have when you have opposites that are added together. So one positive and one negative. You see right here, there's an illustration using the integer tiles. This is considered a zero pair. So whenever you add opposites together, you are always going to get a sum of 0. So whether it is variables or integers. So this particular integer right here is, let's go ahead and, no, it's blue. That's nice. Okay, so this would be like us saying 1 plus a negative 1. Those two numbers are opposites. Their sum is 0. It could be any number, though. It could be 4.25 plus negative 4.25. And since those two numbers are opposites of each other, their sum is always going to be 0. Now we take the algebra tiles, and if you recall, when I'm showing you the algebra tiles, if you were to be manipulating these in class with the actual manipulatives, you would have one side that would be a unique color, and the other side would be red. And the red side is, we often call it as the negative x, and this is the positive x. But as we're going to see in this lesson, since we don't know what x is, we don't really know that this one's always going to be positive or this is always going to be negative. So we're just going to say that we have the value for x, and if we add it to its opposite, it really doesn't make any difference what x is equal to, right? If x was 1, the opposite of x would be negative 1. If x was negative 4.25, then its opposite would be positive 4.25. And regardless of the value of x, if you add x to its opposite, negative x, you will always get 0 for an answer. Okay, so it doesn't matter if it's 2x's plus 2 negative x's, makes no difference how many of them there are. Just if you're adding opposites, you will get 0. So in the previous lessons, you simplified and rewrote algebraic expressions. In this lesson, you will continue to explore various ways to make expressions simpler by finding ways, or finding parts of them that make 0. 0 is a relative newcomer to the number system. Its first appearance was as a placeholder around 400 BC in Babylon. The ancient Greeks philosophized about whether 0 was even a number. How can nothing be something, right? But at some point, we started to figure out, well, if we're going to eventually talk about negative numbers, we have to account for nothing. At least having nothing is better than owing money, right? And so that's where 0 is actually a greater number than a negative number. So I digress a little bit. Let me come back to the script. East Indian mathematicians are generally recognized as the first people to represent the quantity 0 as a numeral and number in its own right, about 600 AD. And here I had heard that it was the Mayans, but I don't know. I'm sure a lot of different cultures had a lot of different representations for the same thing. So 0 holds an important place in mathematics, both as a numeral representing the absence of a quantity and as a placeholder. And by placeholder, it's like, okay, if you've got the number 0 there, that's like 5 ones, 0 tens, that's a placeholder, and then 1 100. So there's the placeholder. And then an absent of quantity would just be like, how many gold bars do you have right now? I have 0 of them. So there you go. Those are those two main ways that we use the number 0 in mathematics. Did you know there is no 0 in the Gregorian calendar system, the one that we use right now? Until the creation of 0, number systems began at 1. And that's why we start our numbering system with what we call counting numbers, as opposed to whole numbers, and 0 is included as a part of the whole number set. So consider these questions below as you work today. How can I create a 0, and how can I rewrite this expression in the most efficient, in other words, simplest way? All right, so the concept of 0. These are some good questions for us to wrap our brains around as we're thinking about the meaning of the number 0. 0 is a special and unusual number. As you read about or read above or in the previous slide, it has an interesting history. What do you know about 0 mathematically? These questions will help test your knowledge. All right, so this is what I'd like for you to do. I want you to pause the video. I want you to read through these questions, and I want you to formulate a little short answer, no more than one sentence. Maybe the sentence only has to be a few words, depending on how much detail is necessary. Okay, so take the time to think about each one of those questions and write down a little response for A through F. I'll pause and take a little break myself, and when I unpause it, we'll reveal each one of my thoughts on this. All right, let's see what we've got here. It says if two quantities are added and the sum is 0, what do you know about those two quantities? Well, remember, that's what we talked about at the opening. Whenever you add opposites together, you get 0 for an answer. So if you know, this would be like the converse of that rule. If you know two numbers have a sum of 0, then they must be opposites. The numbers must be opposites. So, it could be 5 and -5. Their sum is 0. Could be -2 and +2. Their sum is 0. So if you know the sum of two numbers is 0, the only way that can happen is if these two numbers are opposites of each other. If you add 0 to a number, how does this change the number? Well, let's see. If we took 4 plus 0, how would that change the 4? The answer is it wouldn't. It doesn't change anything when you add 0 to a number. And this, by the way, is what we refer to as the identity property of addition. The identity property of addition says anytime you add 0 to a number, it does not change its value. By the way, this would be considered the inverse property of addition. Whenever you add opposites to each other, the sum is always 0. And to be honest with you, both of these properties come into play when we're solving equations, which we're going to get to in a little bit of a later lesson. But if I said to take x plus 5 was equal to 6, the algebraic way of showing this process and how to get the value for x is to take whatever this number is and add its opposite to it. Whatever you do to one side of the equation, you do the same thing to the other side of the equation. Now, you're looking at this, you probably already know what the answer is, right? X has to be equal to 1. Well, what did we do here? Well, first of all, I added the opposite to a number because whenever you add opposites to each other, they always give you 0 for an answer. And so if I added the -5 to one side, I'll add the -5 to the other side, and that ends up giving me 1. Now, we have x plus 0, right, because that formed a 0 pair, is equal to 1. But now the identity property says if you add 0 to a number, it doesn't change its value. So there's no point in saying x plus 0 is equal to 1. Just say x is equal to 1. Because if x is equal to 1, 1 plus 0 is 1, right? So x has to be 1. So we're using both of these properties when we solve an algebraic equation like this. We form the 0 pair by adding opposites, and then that 0 gets added onto our variable, which means that whatever the answer is the value of the variable. All right, moving on. See, if you multiply a number by 0, what do you know about the product? Well, pick any number, multiply times 0, what do you get? What is 3 times 0? It is equal to 0, right? What is -2 times 0? I'll put a little dot there for this one. That's going to equal 0 as well. So anytime you multiply a number times 0, its answer is always 0. And this gets us to another property that gets used quite a bit in algebra called the zero product property. which states that anytime you multiply anything times 0, you get 0 for an answer, which also helps when eventually we get down to part E. But let's not jump ahead. What is the opposite of 0? Well, there are two ways to think about this. I tend to think that 0 has no opposite. Some people will say, no, 0's opposite is the number 0, because when you add 0 to 0, you get 0 for an answer, and I would agree with that too. But I just tend to think of 0, like opposites are when one number is a positive and the other one is a negative, and their sum is 0. That's how I tend to think of opposites. But I guess 0 plus 0 is 0 too, so 0 could be the opposite of 0. But that would be the only number where its opposite is the same. So yeah, just a little bit of a weird concept there. And then E, if three numbers have a product of 0, what do you know about at least one of those numbers, right? So if we took three unknown numbers, x times y times z, and we know that the product of all three of those is 0, that means that x has to be equal to 0, because whatever these two multiply together, they're going to get multiplied times 0 and give you 0 for an answer. Or y is equal to 0, or z is equal to 0, or maybe two of them are equal to 0, and it doesn't matter what the third one is. So this is another example of 0 product property. No, why does that say products? It's supposed to say property. Sorry, I'm going to fix it. This is in class where people would be raising their hand, demanding that I make that change. Okay, 0 product property. So yeah, so if three numbers have a total product of 0 after multiplying them all together, then at least one of the numbers has to be a 0, but it could be two of them or all three of them could be equal to 0. And then the last question, is 0 even or is it odd? And some people's most common wrong answer is that it's neither even nor odd, but really it's an even number, because the definition of an even number is if you take that number and you divide it by 2, you'll get 0 for a remainder. Odd numbers always have 1 for a remainder. So here's an example of an even number, because 2 divided by 2 is equal to 1 with no remainder. Whereas if you took 3 divided by 2, you'd get 1 with a remainder of 1. Or if you took 5 divided by 2, you'd get 2 with a remainder of 1. So what happens when you take 0 and you divide it by 2? You get 0 for an answer. There's no remainder, which means it's an even number, okay? So all the even numbers always are divisible by 2 with no remainder. Those are all even numbers. All of the odd numbers, when you divide it by 2, you always get a remainder of 1. All right, let's start doing an exploration of positive and negative tiles. When you use algebra tiles, positive 1 is represented with algebra tiles as a shaded small square and is always a positive unit. So if we go, let me just see if I can find, okay, so notice all these. You've seen all these before. Anything that's a unique color is going to be considered the positives, right? So positive 1, the kind of aqua blue, the purplish color, green color, all those are considered the positives. And all the reds are considered their opposites, okay? So, I mean, I don't know, do we call them positives? I know this one would be a positive, but is that always going to be a positive? No. Is this always going to be a positive? Actually, it is, because, well, we'll get to exponent rules at a later date. But at any rate, when you see it shaded in, that's always representing what we're calling the positive values. And when it's open or white, that's the same as using the algebra tiles and having them be the red, which signifies kind of like a negative or an opposite. Okay, so the opposite of 1 is written as -1. That is an open small square or a white square. So now what happens when we have x's? The variable x tile is shaded, but is the number represented by a variable such as x always positive? And the answer to that is no, it's not always going to be positive. I just like to think the shaded value of x, or the positive, quotation marks around positive value of x, is just its real or actual value. So then when you look to B, the opposite of the variable x is written as -x. or the opposite. The minus sign means the opposite of. Or the opposite of x. And it looks like it might be negative, but since the opposite of a variable can be any number, what can you say about the opposite of the variable x? So here, here's a great example. -2 is the opposite of 2. But if x were equal to -2, then this would be equal to +2. So just because it's white in the books or red when we're using the manipulatives doesn't necessarily mean that our variable is going to be opposite. So the opposite of x could be a positive or a negative, or technically it could be equal to 0. If x is equal to 0, then the opposite of 0, right? Okay. So is it possible to determine which is greater, x or -x? Well, that's interesting. Let's think about this for a second. If you've got x or -x, if x was equal to 3, this would be equal to -3, correct? And so that would mean 3 would be greater than -3, so x would be greater than -x. If x was equal to -7, the opposite of it would be +7, which would mean that in this case, x would be less than the opposite, or -x. So without knowing the value for x, you cannot determine which one is greater, x or -x. You have to know the value of x first before you can determine whether x is greater than -x or -x is greater than x. And then the last one, what is true about 6 plus -6? Well, we know those are opposites, right? And they form a zero pair, so they must be equal to 0, correct? So what must be true about x plus -x? X plus -x is going to be equal to 0 as well, because it doesn't matter what x is equal to, -x is always its opposite. So if you're going to add those two together, you're going to get 0 for an answer. If you take and add the -7 and the 7 together, then they would make 0. So no matter what x is, -x will always be its opposite, and when you add those two together, they will always equal 0. So there is this thing, a resource page for an expression mat, which, to be honest with you, isn't much different than having a blank piece of paper. So I never print these out for students, and I'm not attaching this. There's no reason to have this expression mat resource page available to you, especially since we're not really going to be using algebra tiles. But keep in mind, you can always go to the online book and you can use the student tool. So let me pause for a second and pull it up and show you. All right, so here we are at problem 105 for lesson 4.3.3. And here is what the resource page looks like. Hooray, a big rectangle. Useless if you ask me, but okay, let's just move on. And now for this exercise, if you want to pull up the algebra tiles, pull up the algebra tile, there you go. Now we can pull these guys in here, manipulate these all we want. And if you decide, oh, I don't like those, just highlight them and hit the delete button and they can go away, and you can build these expressions using this tool, okay? I'm going to use what I like to use, and that is my software. Okay, so let's read through the directions. From your work in problem 104, you can say that situations like x plus -x and 6 plus -6 and x plus -x create zeros. That is, when you add an equal number of tiles and their opposites, the result is always going to be equal to 0. The pairs of unit tiles and x tiles shown in that problem are examples of 0 pairs. All right. What you're going to do is we're going to take these two expressions, and I want you to write them down. I would like for you to build them in that student, in the tool with the algebra tiles in the online book. Definitely copy this down, and some students just draw the pictures of them. You can do that as well. Just keep in mind, when you're drawing the pictures, if you're creating an X tile, kind of lightly shade that in. That's an X tile, perfectly drawn, right? And if you're going to draw a -1, you would draw it like that. If you're going to draw a +1, you'd make sure you shade it in this one as well, okay? In fact, you might be able to even darken these in a little bit more. I don't think we've got any Y's that we're working with in here. So you know that the skinny rectangles are always going to be X's, and the small squares are going to be the unit tiles, okay? So what I'd like for you to do is go ahead and build these guys and copy down these two expressions for problem A and B, and then I want you to manipulate these so that you can put all the zero pairs together. And then whatever's left over that is not fitting into a zero pair, that's your answer. Just combine those together and write down the expression in the simplest form, okay? So let's give you a couple minutes. Go ahead and sort through those. And I believe this is the last problem for today's lesson. So make it nice and neat and record your answer, and then I'll do the reveal to see if you're getting your answers correct. All right, so this is what I would have had you do in class. I would have you rearrange these guys, and so, you know, you got your 2 1s over here, so I'm going to bring over a -1 to match up with that guy, and a -1 to match up with this guy. And I'm going to leave this guy here. I'm just going to collect all the zero pairs over here. Now I'll manipulate these guys and bring in a -x, another -x, and another -x. So what we eventually have here is 0 plus 0, 0 plus 0 plus 0, plus -1. So our final answer has to be -1, right? So when we simplify this entire expression, it ends up being equal to -1. Now let me show you how I would do it if I was highlighting. I would take all my x's together. Notice how you got 3 x's there to match up with those 3 -x's. Well, these guys cancel out with that guy. And then you have your 2 and your -3. And so now answer that question. What is 2 minus 3 or 2 plus a -3? It's equal to -1. Up for B, what do we have here? I'm going to move this guy here, and I don't have any other zero pairs, so I'm going to move this -1 over to here to be with the other negatives. And then this x matches up with that -x, and then I'm going to move these guys over to here. And honestly, it doesn't make any difference if you have the x's on the left or on the right, but this says 0 plus 0 plus 3 x's plus 6 -1s. So our final answer ends up being 3 x's plus -6, or 3x minus 6 if you wanted to do the reversal KFC and change that back to a subtraction problem. Okay, so when we are combining like terms, we now have to be aware of the fact that you're going to be combining like terms, but you're going to be adding positive and negative coefficients together. So 2 plus a -1 plus a positive 2 is 1 plus 2 gives you 3, so that gives you the 3 x's here. And now the last part is just doing our integer operations. -2 plus -5 is -7, and then -7 plus a positive 1 gives you -6. All right, so that ends today's lesson, and tomorrow we will pick up where we left off, and we'll just bring all of this together, are using distributive property, combining like terms, and in the process of combining like terms, zeroing out the zero pairs to help us simplify these expressions completely. All right, so I guess your next step is to head over and complete your homework. Take care, bye.
Hey, feeling good, like I should. When in dark, I walk around the neighborhood.